So I'm a retired electronics engineer, and I spent a lot of time debugging electronic circuits around Europe. And often the device drivers that were controlling the circuits were a source of the problem. So I'd be working my way through all the electronics on the board, trying to figure out what was wrong with it, then gradually work my way up to a driver. And from that, I got an interest in learning how to write Linux device drivers. It was sort of an itch, really. And also some of the software that you might want to use to control those drivers. So I started experimenting really on a Raspberry Pi. That seemed like a good vehicle to do it on, mainly because you can easily attach hardware to it. So what I've done is, with the help of a friend, we've developed a simple web test page, and using a Raspberry Pi 4 connected to connected to an LED and a switch. I've developed a simple GPIO driver which connects to this web application. So the idea of the switch is to generate interrupts to the driver. So when an interrupt is generated, then the driver will toggle the LED. The idea of the web app is to allow you also to control the LED to switch it on or off. So this whole project is just really a learning exercise, how to build up a stack of software from the user side using a mixture of HTML, Python, and then within the Linux kernel, develop a driver, which is written in C. So generally all the drivers in Linux are written in C because Linux itself as an operating system is written in C. So on the user side, what we have the driver test page, and that's going to be on its own little network at 192.168.2.7. Then we're using a Flask barebones server, which we call up with the help of a Python script. And then we have the actual LED control script. So we have these three boxes of software effectively, and they follow this pattern called an MVC design pattern, model view controller. That seems to be quite a common pattern for when you're developing applications that control stuff. So the view itself, the page, that's written in HTML. Then we have a thing called the controller. It's a bit different from the controller in the previous talk. And that calls up the server. And then the actual script that is controlling the LED light is just a separate script. In the kernel itself, we're going to load a driver. So that's something that we've written. And this driver can basically drive GPIO pins, and it can also handle interrupts. So this runs in kernel mode. And then that directly controls the GPIO registers in the Raspberry Pi 4. So that's the basic stack. So the idea was to develop that sort of stack and then use that as a basis for further development later on, just to get all that working, really. So let's have a look on the user side first. We have at the top there, we've got the so-called web app, or the MVC, this model view controller type design pattern for the app. That controls the LEDs via a device file. So this is a very common way of interfacing to a driver in Linux. You have a device file in the /dev directory. And these device files, they basically represent devices and drivers as files. That's the old Unix philosophy of everything is a file. Which means that you can use operations like read and write as if you're reading or writing to a file. But what will happen is that the driver will see those read and write system calls being made to the device file, and then interpret those as reading and writing the GPIO registers. But as far as the user application is concerned, it just thinks it's writing to an ordinary file. So you can use the same read and write commands that you'd use writing to a text file as if you're writing to a piece of hardware. When we're doing that, the kernel runs in what's called process context. Later on, when we start generating interrupts, the kernel will switch into what's called interrupt context. In interrupt context, it stops whatever it is doing in process context. So all user processes basically go to sleep for a while, and then it'll handle the interrupt and try and do that as quickly as possible, and then go back into process context. So that's one reason why when you're dealing with interrupts, if you want the kernel to do it, you would deal with that interrupt in the driver itself, rather than maybe in a user program. If you're dealing with the interrupt in the driver itself, you can deal with it very, very quickly. If you want to propagate the interrupt to a user process up in user land, that can take much longer because you don't know when the CPU is actually going to deal with your user land process. So quite often for sort of critical interrupts, you would deal with those in the driver. The device file itself, over here, is actually created by the driver. So when you load the driver into the kernel, it'll set up that device file. The model view controller concept, the idea basically is that you have a box called a model, piece of code. In my case, that's the actual thing that talks to the driver. Then you have another piece of code or a box, which is called the view, which is how the user sees the system. And so typically that's an HTML file. And that will contain the buttons and the displays and so on. And then linking those two boxes, the model and the view, you have a thing called the controller. So this is a sort of standard concept. The controller itself, in our case, it'll call in the Flask barebone server, and it'll talk to the model box, and it also talk to the view box. But it doesn't really know what each of those do. So yeah, the advantage of this sort of approach is it's kind of a division of labor. You can change what's in each box without affecting too much of the other boxes. Pretty much that controller code is kind of the heart of the web stack, really. So my directory structure for this model view controller concept, I have a thing called controller.py. We'll have a look at a bit of the code in that in a minute, which calls in sets up the barebone server. Then we have a script called ledOnOff.py that interfaces directly with a device file and hence the driver. And there's a directory called templates, and that contains your HTML files. If it's just one page, you really only just need one HTML file in there. So I have the controller itself will set up a local network address for it's running on the actual Raspberry Pi. And so whatever network address you've assigned to that to your Raspberry Pi, that's what it will use. And it'll use a port address of 5000. As I mentioned, the script which controls the LEDs, that's ledOnOff.py. And the controller will talk to that. And I have a directory called templates, which will contain my web page code. We have a quick look at some of this. Let's have a look. I don't know how visible that is. It's a bit hard. It's a bit harder to make this any bigger, unfortunately. I don't know if you might be able to see it on a laptop screen at home. So the actual LED on off script, it's quite small, really. We have a function called query. So the controller will use that every time on the web page itself, somebody wants to query the status of the LED, or the page wants to display the status of the LED. It'll tell the controller to get the status of the LED. And the controller in itself will use this query function to read the GPIO registers. Essentially what we do, we open the LED device file or the driver device file, and then we issue a system call called read. And these system calls in Python, they're very similar to any other sort of system call you might use in any other sort of programming language. Likewise, if we want to use the web page to turn the LED on, again, we open the device file, and then we send it a 1, which we have to convert to a byte, so that because the driver itself is written in C and it deals in bytes, it needs to see what's coming down as bytes. And then we close the file, the device file. And again, likewise, when we want to turn it off, similar sort of thing. We send a 0 to the device file. The driver will see that and then turn the LED off. So this is just a very short Python script. And that in turn is used by this much bigger Python program called controller.py. At the top, we've got a whole bunch of imports here to do with Flask, this bare bones server. We also import our local LED on-off Python script. And let's go down to the bottom. Here at the bottom is essentially where we render the web page. So this render template function essentially updates the web page, whatever the latest information is. So using Flask, it's very easy to basically set up a very simple bare bones server and have a web application. And then the actual HTML file is quite short. And what I've had to do at the top here is I had to put a refresh statement in there so that the page refreshes itself every 1 second. At the moment, I've set it for 1 second so that it can check to see if anybody has switched the LED on or off. And here, basically, I set up the buttons of the web page itself. That's the web. So we've discussed the user side there. The other way we can turn that LED on and off is through this switch here. Every time we press that switch, it will generate an interrupt to the Raspberry Pi. So we have to have some interrupt handling functions in the driver. And when that interrupt occurs, as I mentioned before, the kernel then runs an interrupt context. So it suspends whatever else it's doing and then tries to deal immediately with the interrupt condition. So all user programs are basically suspended in that sort of context. Now, one of the issues we've got with a sort of push button switch, I've got a very crude switch here. It's a very cheapo thing. So when you press it, the contacts, they bounce around a lot. So, and the Raspberry Pi 4 doesn't have a debounce function in it. It doesn't support one anyway. So you can either do the debouncing hardware or you can do a simple sort of crude software mechanism, which is what I've done really. So every time I see an interrupt, it then triggers a delay in my interrupt function that's servicing that interrupt. And I wait for a certain amount of time to see if all these spikes have died down. And then I'll check to see if there's a real interrupt there.
So it doesn't really work that well, as we'll see in a minute. So, but uh, but there, but the idea was really just to show how interrupts work. So typically, the way interrupts are coded in drivers is something will generate an interrupt. In this case, the GPIO registers in the Raspberry Pi, they have a thing called an event detect bit. So you can set up different interrupt conditions. You can do rising edge, falling edge, high level, low level, and you can set those as interrupt conditions, and then the relevant interrupt detect bit will then trigger when one of those conditions happens and generate an interrupt to the interrupt controller. So when we get an interrupt, the sort of normal way of coding this in Linux is that you have your interrupt routines actually consist of two routines. There's a routine which is called the top half interrupt service routine. And that's the sort of terminology that's used in Linux. You have top half and bottom half routines. The top half, it will do all the urgent work. So basically, this should ideally complete depending on your system, in less than 100 microseconds. Or even if you've got a busy system where there's a lot of interrupts going on, so you're controlling a lot of hardware and they're all generating interrupts, you want this top half interrupt service routine for your little bit of hardware to complete in probably less than sort of 10 microseconds to stop holding other things up. Because remember, every time you're dealing with an interrupt request, you're stopping a lot of other stuff from working. So normally what you do in that top half, you just acknowledge the fact, you acknowledge the hardware that sent you the interrupt, and then basically say, okay, I've seen your request. Now leave me alone, and I will deal with you. And then the top half schedules what's called the bottom half interrupt handling function, and that does the remaining work. So in my case, what it will do, it'll do that filtering or that delay just to check if the spikes have settled out, because you might have a delay of a couple of 100 milliseconds in there, and you don't want to put a delay of 200 milliseconds in your top half interrupt routine. That would hold up the microprocessor far too long. So you put that, you schedule anything which is going to take some time into this so-called bottom half here. The bottom half itself, depending what type of bottom half you use, you can still run that in interrupt context, but it would be called what's a soft interrupt context. That means whenever another hard interrupt comes in from somewhere else, that bottom half will be suspended for a bit. But it'll still have a higher priority than the user process. So we'll have a quick look at a demo. So normally the way I load my driver, I've got a make file that does that for me. I just type make load, it loads my driver into the kernel. I've already set this up, so I've loaded it into the Raspberry Pi. I run a second terminal window where I look at all my kernel messages, so I can see what my driver is doing. And in another terminal window, I'm going to run this controller.py. So I've already got all this running at the moment. And that will set up the web server. And all we have to do in the browser is go to the web address, go to the IP address of our Raspberry Pi. Right. This window here That's a terminal into my Raspberry Pi. Can't actually show, I don't know if I can show you the Raspberry Pi from here. No.
Turn on the video. Zoom.
On Zoom, right?
Shit's on now. Is it? No, it's on.
Yep.
It's not really best.
Is that on your, is that connected to? Oh, it should be.
No,
Oh, all right. I need to go to these video controls on here.
what is in Zoom?
Oh, it's in Zoom. Oh, okay. Start video.
I don't know.
Oh, there we go.
It's, if it changed the video. It's your laptop video.
Yeah.
No, it's your laptop.
Oh, I see.
Well, just in Zoom. Zoom should look like.
Oh,
video.
Zoom should look. Oh, yeah, it's still, oh, here we are.
Yeah, stop. Oh yeah, just change to be Sonic. Yeah. Yeah.
Oh, there we go. What can be seen? Oh, yeah, I can see it, but then you can't really see it on the screen, though, can you? Oh, I see. You can see it up there. Oh, okay. All right. Yeah. All right. It's all right. It's okay. It's a yeah, simple breadboard there with the switch and the LED. And if we look at um, this window here, so this is just currently displaying kernel messages from the kernel message buffer. There's a command called dmessage you can type, and that will display all your kernel messages. On the slides, you can see the exact format of that command. So at the moment, it's the web page itself is running. I'll just show you the web page. So that's the driver test page there. So let's press turn off. Turns the LED off. And then if we go back to the terminal window, then what you're seeing here all the time, you're always seeing context process. This is because the web page is every second it's interrogating the status of the LED via that controller.py program, which in turn is writing to the driver. And every time the driver itself sees a system command, like read or write coming from a user process, it knows it's in process context. So it's printing me a message to say, I'm in process at the moment. And if I generate an interrupt, you might have just seen something called hard IQ there, which is hard interrupt. Not that easy to see, but that's the context then. And then very briefly, you might have also seen something called soft IQ. Yeah, soft IRQ. So again, it's still an interrupt context, but now it's moved into a soft state, which means other hardware interrupts can interrupt that driver. So this gives you a very sort of low-level view of what's actually happening in the kernel itself. So sometimes when you're debugging hardware and you've got some process running in user land, it's transmitting commands through various stacks down to a driver in the kernel, and you don't know why something isn't working. you can go into the kernel message buffer and actually get quite a lot of information to see what's going on. And then work your way back up from there. Go back to the, so if I now just switch the LED on and the web page has gone back to on. I'll switch it off, go back on. So it's a very simple stack there, but there's quite a lot of software just to switch an LED on or off, basically. But the driver itself is also quite a lot of code just because of the interrupt handling. There's actually does bring up some quite interesting asynchronous concepts, which we sort of touched on in a previous talk back in January, which is let me go back to the fact that you've got an interrupt button down there, which can turn the LED, which can access the GPIO registers, and also that this user process can also access the GPIO registers. You've got two things going on that can access the registers at the same time. So in your driver code, you have to make sure that that doesn't cause any sort of corruption of the registers when you've got something like that going on. So there are techniques you can use to make sure that, for example, when an interrupt is going on, it's accessing the GPIO registers, nothing else is going to access those registers at the same time. Or when the user process is accessing the registers, it's got exclusive access and nothing else is accessing those registers as well. And all of that sort of synchronization has to be handled by the driver, essentially. So that was sort of another interesting aspect of this sort of project, is how you make sure that multiple accesses to the same piece of hardware or same resource doesn't cause a sort of system corruption. So we have to get into all of that as well. So that's what we basically have here. It's a sort of a very simple stack that we can use to build other projects from. That's pretty much it, really. If you've got any questions? Yeah. So let me just go back to that. Everything is you want to. I'm on Facebook as well. If you've got any questions about the driver, so here's the resources. So the presentation, the code samples, they're in my GitLab repository at Raspberry Pi. So on April the 30th, 2024. And these slides, they'll also be on Facebook so you'll be able to see these resources. So the way the code folders are organized on there, you'll need to change some of the path names in the make file. So all the make files are there and all the code is there. But the path names are in the make files. They relate to my own sort of directory structure that I use for development. So when you set this up on your system, you'll need to probably change some of the path names in there. But it's all fairly understandable. The actual Flask framework, that's pretty easy to install as well. Before you use that, just type this command, pip 3 install Flask. There's quite a lot of tutorials on it. You can use the code on my GitLab site as an example for setting up a Flask server, and then just develop a simple web page with it. I'm mainly actually a C coder, so a lot of the stuff in Python and HTML, what I did, I looked at what other people did, kind of just sort of adapted it. I didn't try and learn Python or HTML from scratch. I sort of just use my C logic to figure out how other stuff work. I suspect a lot of us work that way. Yeah. Yeah. All right. So the reason for using a driver is really speed. If you're using a driver, you're doing things much more in real time. So any interrupt handling is virtually in real time. If you're going to deal with you can propagate the interrupt if you want up to user space. In other words, you see a signal coming in from a piece of hardware and just say, okay, there's something here, and send it up to the program in user space. The only problem is you never know exactly when that program in user space is going to be serviced by the CPU. It's up to the CPU scheduler to decide when it's going to give your user program some time. But if you deal with it as an interrupt, the CPU basically has the CPU core that gets that interrupt. So if you've got a multi-core system, that interrupt will go to one of the cores. What it will do in the initial hard interrupt case, it'll disable all the interrupts on that core, plus all the interrupts on the other cores as well. No, doesn't disable the interrupts on the other core. What it will typically what happens is when you get an interrupt, you decide which core is gonna service it. Or the Linux operating system will decide which core will service it. But that interrupt, then in this case, that one's coming from the GPIO registers, that will be blocked on all the cores until that interrupt is serviced. And then on the actual core itself that is servicing that interrupt, it will block also all other interrupts. So that the CPU isn't bothered by any other interrupts on that particular core. And then also it'll send all processes in user space to sleep. They will also, won't be for very long, but essentially the scheduler will just now deal with that particular interrupt service routine. So it means that interrupt will get dealt with very quickly. So you might have some critical interrupts. It could be, for example, you're measuring a level of something, of a dangerous liquid, and that liquid level is going too high. You don't necessarily want to wait till that emergency level is signaled somewhere in user space. You might want some real-time action taking place on that. In which case you deal with that within the driver itself, and then you get a very quick turnaround of dealing with the situation. If you're doing something like what's called polling, that you probably want to do in user space. But polling is just whereby it's another way of looking at what the hardware is doing. So instead of the hardware saying, I want to be serviced, the hardware will wait till the user interrogates it. So you say maybe poll it every 100 microseconds or something and say, have you got anything for me? Have you got anything for me? So you would use something like that for situations which aren't critical. But anything where something needs to be dealt with quickly, you use hardware interrupt. For example, things like Ethernet communications, that generates millions of interrupts. Every time there's a packet available, it generates an interrupt to the CPU. So look, I got something here. Can you take this packet off? We'll deal with it. And if the driver wasn't dealing with that directly and waiting for user space to deal with those packets, it would slow the whole network down. So that's really the sort of concept behind interrupt handling. Sorry?
Efficiency there. Drivers do nothing until something happens.
Exactly. In fact, drivers work like it. Yeah. Exactly. Yeah. Normally, you would poll from user space. You can get a driver to poll, but it's a waste of time, really. Yeah. Yeah, you're right. Yeah. Exactly. Yeah. Yeah. In fact, when you look at how drivers work, it's very different from programs in user space. Drivers are just bits of code that just sit there waiting for something to happen. Either they wait for a user process to send it a command to do something like to read or write a piece of hardware. So most of the times they're basically just sitting there. Whereas a user program, you normally got something happening from start to finish. When you're writing a driver, what you're really doing is you're just populating it with lots of functions, each of which kind of sits around doing nothing until it gets a system call. So the driver then sees a system call coming its way. It says, oh, okay, what's that system call? Oh, it's a write system call. And it goes to what it's called its write method. And then within its write method, it says, okay, I've got to write all these registers. That might be one example. Or I've got to send some data down a wire. Or I've got to read some data from a wire if it's a read command from the user space. So the driver has what's called a set of methods, and the methods are all very hardware dependent. As far as the user space processes are concerned, they don't really care what any of these methods are like. They've got no idea what the hardware is up to. They just see everything as a file. So all they have to do, the user space processes, is send these very sort of standard system calls: read, write, open, close, as if everything is a file, basically. Any other questions?
Suppose you can't run you try script access to GPIO at the same time.
What you do, you use a technical spin locks. So
Because the scene in your code that to basically initialize the GPIO.
yeah,
When you do the GPIO.
yeah.
So suppose if this file is one, and then you want to run it, I can get up maybe 6 strip of LEDs onto that at the same time.
You can. So the driver, as soon as the LED script wants to access the driver, that's no problem. It'll send a read or write system command. Let's say it wants to turn the LEDs on, it'll send the write command. So we're writing to the GPIO registers. As soon as my driver sees a write to that GPIO registers, what I then do, I activate what's called a spin lock. And that locks out any other process from accessing those GPIO registers. And the reason why it's called a spin lock is any other process that tries to access those registers are sent into what it's called a spin. Basically, they're going to wait there at the door effectively. So the CPU is letting those processes essentially, it's called spinning. It's similar to sort of sleeping, but they just wait there. And meanwhile, the CPU core, that is, let's say you've got a 4-core system. And one of my cores is currently dealing with accessing the GPIO registers to turn the LED on. And then another core is trying to access those registers as well. Then, because my first core has already grabbed those GPIO registers and set a spin lock, the other CPU core sees that and then just spins on itself. It's just waiting there. Spinning clock cycles, essentially. That's where the spinning comes from. And then when my first CPU core has finished, either the driver is finished using those GPIO registers or something else is finished using them, then that spin lock is released, and that second CPU core will grab the lock and then stop any other core accessing those registers. And so I've got those locks set up in my driver to enable the CPU cores to do that. And that's quite a common way of doing that. So you can you just have to be very careful how you use those spin locks, because you don't necessarily want to put everything in a spin all the time, because then you're wasting CPU cycles. So you have to be a little bit careful how you use them. They're quite a powerful weapon. So sorry?
You can do like HTTP request.
Yeah. Not within the driver. No, you try and avoid that sort of thing within the driver, because then you're opening yourself up to a lot of viruses. Yeah. Once you're writing software within the kernel, anything like drivers, you've got complete access to the whole system. Everything, any programs that are written in user space, they're all sandboxed. They get a bit of virtual memory space in which they run, and outside they can't grab anything else. But any driver or any software that's running within kernel space has got access to everything.
So what's the logic? What would be the logic to, let's say you support a light up when you want to call and then endpoint? How would you create a driver that does that?
Oh, that's a good question. You want to call some sort of endpoint? Yeah. Well,
Is that possible, or you need to have a this Python script that can pulls information?
It would be possible. I mean, yeah, you can send information over networks. Yeah, you could set up a low-level driver that communicates over a network. Yeah.
What we have two drivers.
We need a driver at each end. Yeah, you'd have one driver. You could do it all in one driver. Yeah. I mean, you could do mean, that's sort of what simple UART drivers do, for example. They either they can loop back over a network. Yeah. So you could do that. Yeah. So you could have packets, or even serial data. Yeah, or you could have serial information, for example. So you could set up basically a buffer within the driver. And that's probably what you do. You set up buffers anyway. You can you put some data in there. Either the hardware can put some data into that buffer. You've got some hardware which is generating data, puts it into the buffer. And when the driver sees that data in the buffer, it sends it back out again on another link. So the user never needs to have to see that. If you wanted to do it that way, yeah, you have a sort of secret communication. Yeah.
For example, once you give it to the right channel, and show.
Well, every time you write a driver, it uses what's called header files. The header files, they're the equivalent of what's like the C library in user space. I don't know if you've come across the C library in user space. You may have access. Python. Every time you write a Python script, and you're issuing commands like, let's say you're reading or writing a file from a Python script, you're doing read and write, what's called read and write system commands. They actually get translated to some commands in the C library. So nearly every high-level language actually that runs on Linux will use the C library. And the C library takes a Python, say, system command, and then it will put a C wrapper around it, which contains some assembly code, which then accesses the kernel and sends the commands to the driver itself. So that's what you have in user space. So the C library is kind of the interface from all user space programs to anything that's happening to all kernel space functions. Now, when you're writing a driver, there's a similar sort of library, but it exists effectively in kernel space. And those are called header files. And those header files are very dependent on the version of the operating system. So your driver will work with one version of the operating system. And what can happen is whenever time you get a new version of the operating system, the header files, they change a little bit. And then you have to recompile your driver. Yeah, you could share it. Yeah, otherwise you have to recompile. I mean, typically the header files don't change that much. So when you've got a driver working on one version, then you upgrade your Raspberry, your operating system version, and you recompile it. Mostly it works fine. You just recompile it, you never get a problem. But occasionally something changes a little bit. Yeah. You can normally if you become if you work in, I mean, I'm not a Linux system developer. If you become one of these sort of open source developers and you write drivers for stuff, then what you would do, there's like a whole hierarchy of in the sort of Linux open source world. You've got people who make what's called, there's a hierarchy of maintainers, they're called. So the ultimate maintainer is Linus himself, but then below that, for each, Linux is made up of all these different sort of high-level systems, and there's a maintainer for each one. So, let's say you're writing a video driver, and there'll be a video system maintainer. You submit your code to him or her, and they will check it through, and then effectively certify it. And then it becomes part of the main library of Linux. And yeah.
It's certified. We trust you, and we can load it.
Well, the tricky bit is a lot of companies, when they write drivers, they don't necessarily have it certified by the Linux open source community. They just give it to you. They just give it, and you have to sort of use it on trust, basically. Yeah.
You find a lot of code is actually copy and paste. When you look at driver code, when you download stuff, you'll see how much of it is copy and pasted, because a lot of it is written abroad. So probably the biggest driver writers are in India and Taiwan, and you'll see as hardware goes through goes through upgrades, you might have an Ethernet controller of some sort. When you look at the code for it, you'll see dates in there going back to sort of 1980s, and then each time what they do, every time the Ethernet controller gets upgraded or made faster, they'll use some of that code, add a bit more code to it. So it becomes this huge piece of software, a bit like your genes. It's got everything going back in there 40 years ago. And actually, it does raise interesting security questions, because how do you debug this sort of stuff, because it's all sort of copy and pasted. So what will typically happen is someone will have written the code, he'll have disappeared, somebody new comes along, they just take the whole lot and add some extra bits because they're afraid to break what's there before. And yeah, so you have all this sort of stuff floating around in the kernel, basically. And the other thing that a lot of manufacturers do now, they don't really want anyone copying their code, their driver code, and so they implement it as firmware. And so the driver itself comes with your Linux distribution, but it's all in bytecode, it's all in machine code, and then that gets downloaded onto your Raspberry Pi, for example, as firmware. And the open source community is very unhappy about that, because you're meant to really share everything, but a lot of manufacturers don't want to do that, because if you see their code, then you can see how all their registers work, and it gives you an idea what the architecture of a chip is like, and other people can copy it. So that's always been one of those sort of points. I mean, you find also with the Raspberry Pi, the Broadcom device in there, they hide a lot of stuff, and there's been a lot of trial and error by people in the sort of Raspberry Pi community to work out how the Broadcom registers work and things like that, so that we could write our own drivers.
What do you plan on?
Sorry?
What do you plan on doing with this technique now?
Well, use some more sophisticated hardware. I've got a thing on here which I'm sort of working on. There's it's an I2C device which reads pressure and temperature. So I was going to do an I2C driver. So now that I've done GPIO drivers, which are basically just having drivers which read and write bits. The next thing is to work on a driver that actually works on a bus. That's a lot more complicated. And so just working on that now. So
Planning on building, or you just experiment.
Yeah, getting used to how you write the drivers. Yeah, it's a sort of driver training vehicle.